Hello everyone. So today we will start a new chapter, that is non-uniform flow in open channels. Okay. So far we have studied about uniform flow in open channels and have derived various relations about critical depth, critical flow and specific energy. Okay. These all conditions were derived when we assumed that the flow in was uniform, means the depth and the flow properties and various aspects of parameters of the flow does not changes with length of the channel. Okay, but here in case of non-uniform flow there is condition that it is also called varied flow. Okay, means how the flow can vary actually gradually or maybe rapidly. Okay, maybe a gradually varied flow or it may be a rapidly varied flow. And this is rapidly varied flow. So first of all we will know that non-uniform flow is that flow in which the depth of the flow changes from section to section, in which the depth, that is y, changes at every section along the length of the channel. Okay, then the gradually varied flow is that flow in which the depth of flow varies gradually. Means if we have a barrier over here, a dam or reservoir or anything of such kind, and the flow is taking place over here, then suddenly the flow will, this is not the case actually, if this is the case then the depth is continuously changing. Okay, but we cannot determine the particular point at which the depth suddenly changes, so it is a gradual variation of the depth. So the flow here is gradually varied flow. Okay, examples are dams, piers. Okay, the second type of flow is rapidly varied flow, in which we can observe the change of the depth with a particular precision. Okay, here the depth suddenly changes. Okay, so This is an example of rapidly varied flow. Hydraulic jump is a case of varied flow. What is hydraulic jump? Hydraulic jump is the when water is flowing over its path and suddenly a big obstruction come into its way, then the water suddenly jumps over here and then follows its path. So this is a case of hydraulic jump. Okay, so here we will discuss both types of flow. Okay, means first we will deal with gradually varied flow, and then after we will deal with rapidly varied flow. Or hydraulic jump. Okay, so let's start. Gradually varied flow. Okay, so what is the equation for a gradually varied flow? Okay, the same conditions will be used as in case of uniform flow. What was the condition for? Actually, we will use Manning's and Chase's formula in deriving the equation for gradually varied flow. Okay, so first we will derive a topic which is called a dynamic equation for gradually varied flow. Okay, so first of all we will see the condition that according to Manning's formula, the velocity was given as under 1 by n to the power 100 raised to the power 2 by 3 and slope to the power 1 by 2. So what is the value of slope from here? Slope to the power 1 by 2 is v times n upon r raised to the power 2 by 3, and this 1 by 2 cancels over here and it is a square. So this is the slope equation for the slope, and if we use Chase's formula, then according to this formula v equal to c under root r into s. So what is the value of slope from here? Slope is v by under root c under root r to the power 2. Okay, this is the value of slope. So this is the assumption which is used, and the second assumption which we used in, we will consider that the bottom slope of the channel is very small. Means if this is the channel and it is the bottom and water is flowing over here, then this slope should be very small. What is the meaning of this small slope? This small slope means tan theta or sin theta is approximately equal to theta. This is the meaning of this term. We always have some assumptions regarding this, that slope is very small. Okay, so the meaning of this term is actually we can equate tan theta equal to theta and sin theta equal to theta. This is the meaning of this statement. Okay, the next assumption is that channel is prismatic. What is the meaning of prismatic? Means if we cut the section from anywhere, we will always, if we cut the section from here, we will always get a rectangular channel. Means the cross section does not change along the length. Okay, this is the meaning of prismatic. And we have studied energy correction factor. As unity. Okay, pressure distribution is always hydrostatic. Okay, means the pressure variation at any depth is hydrostatic, means a static variation of pressure. Okay, as we have studied earlier, if pressure distribution is not hydrostatic, then it becomes difficult to calculate the things. Okay, so these were the assumptions that we have for deriving the equation for gradually varied flow. Okay, now derivation part. Okay, so derivation part, we can assume that if let's make a diagram over here. If we have a channel bottom over here, this surface is chosen as a datum surface. Okay, the water is flowing over here, or let's assume a parallel surface. So this is the water surface. Okay, then this term will be depth y, this term is z. So, and the total energy line is over here, and this value will be equal to v square upon 2g. Okay, so this is total energy line. Okay, this is water surface, and this one is bed slope. Okay, so for this flow, the total energy of the flow will be this datum surface z plus this depth y plus this kinetic energy term v square by 2z. Okay, so the total energy is datum surface plus depth plus v square by 2g. This is the total energy of the surface. Okay, so we can write over here h equal to q square upon 2g a square plus z plus y. Okay, because q equal to area into velocity, so we have to put the term v from here to here. Okay, so this is the equation of the term. And now if we differentiate this d total energy term with respect to x, means along the length of the channel, then we get dh by dx is equal to dy by dx plus dz by dx plus dy by dx of q square upon 2g a square. Okay, so this dh by dx is the, what is h? H is the total energy gradient. Okay, means this was the channel bottom, this was water surface, and this is the total energy line. So if we get to differentiate this dH by dx, then we will get the slope of this energy line. Okay, so the slope of this energy line can be written as SF. Okay, and we can see that slope is decreasing in the direction of the flow. So this dH by dx term will be a negative one. Okay, so this dH by dx can be written as minus SF. Okay, which is slope of the energy line. Okay, and it is always a negative one. Similarly, what is dy by dx? Dy by dx is the change in depth along the length of the channel. Okay, and what is dz by dx? What was z? Z was the height of the channel bed from the datum surface. Okay, so this is the channel bottom slope. So the bottom slope of the channel can be written as S naught. Okay, this is the slope of the channel bed. Okay, so the slope of the channel bed can be written as S naught, and this slope is also decreasing along the, this is the direction of the flow, so this slope is decreasing in the direction of the flow. So here it is also written as with a negative sign. Okay, this negative sign indicates that total energy and datum surface decreases as the value of x increases. Okay, or it may be said that it decreases along the direction of flow. Okay, so this term h equal dh by dx equal to dz by dx plus dy by dx plus d by dx of q square upon 2g a square. Okay, so this dh by dx can be written as minus sf dz by dx can be written as minus s naught. This dy by dx can be written as it is, because we are interested to find a critical depth or change in critical depth with respect to x. Okay, and we have to differentiate this term. Okay, so let's deal with this term. It is d by dx of q square by 2g upon a square. Okay, so here if the discharge is constant, the only area is a variable here. Okay, means area which is breadth into depth, so this depth is varying continuously, so this area term is a variable over here, so we will have to differentiate this area term over here. Okay, so let's do it. This can be written as d by dy into q square by 2g upon a square into dy by dx. Okay, this dy and this dy can be cancelled from here, so it is brought into this format to make the calculations easier. Okay, then now this a square term can be written as dy a raised to power minus 2 q square by 2g, okay, into dy by dx. This comes out to be once again, this comes out to be minus 2 a raised to power minus 3 upon 2g to q square to dy by dx into dA by dy. Okay, let me write it clearly. Means this comes out to be minus 2 a raised to power minus 3, okay, into dA by dy. Okay, so putting this term in this here, we will get minus 2a to the power minus 3 dA by dy to q square by 2g. Okay, so this 2 and this 2 gets cancelled, and this dA by dy term, okay, let's write over here. This 2 and this 2 gets cancelled, so it is written as q square by 2g a cube into dA by dy. So what is the value of this dA by dy? Okay, means dA by dy can be written as d into top surface into depth upon dy. Okay, this top surface is a constant, so it comes out over here, and this dy gets cancelled, so this dA and dy terms is nothing but a top surface. Okay, so this expression is q square t upon ga cube. Okay, so writing it in previous equations of dh by dx equal to dz by dx plus dy by dx plus dy by dx into q square t upon ga cube. Okay, so this was minus sf, this was minus s naught, this was plus dy by dx, and this was minus q square t upon ga cube into dy by dx. Bring out this term over here, so this term gets sf plus s naught equal to this term. Then taking this dy by dx as a common, we will get dy by dx into 1 minus q square t upon ga cube s naught minus sf equal to, so the equation that we derived over here is s naught minus sf is 1 minus q square t upon ga cube. So what is the value of dy by dx here? Dy by dx is s naught minus sf upon 1 minus q square t upon ga cube. Okay, now what is this q square t upon ga cube? If this is equal to 1, then we get critical flow. Okay, so what is the value of this one? This one is actually nothing but a value of Froude number, which we have already derived earlier. Okay, so this q square t upon ga, so putting over here we get dy by dx equal to s naught minus sf upon 1 minus Froude number square. Okay, so this is the dynamic equation for gradually varied flow. Okay, if we have this dy by dx equal to 0, means if the depth is not changing along the length of the channel, this dy by dx equal to 0, so we get s naught minus sf equal to 0. This means s naught equal to sf. What does this mean? This means the slope of bottom of channel is equal to slope of energy line. Okay, means they are parallel to each other. Okay, at critical flow. Here one thing is to be noted: if dy by dx is positive, means if the depth of the flow changes along the x-axis, then water surface is rise. Okay, means what does it mean? Means if this x direction and the depth is, means dy by dx is positive. Okay, means depth is continuously increasing along the length, so in this case the profile of the flow will be rising, hence water surface will rise. Okay, if dy by dx is negative, means along the depth of the flow, along the length of the flow, the depth is decreasing, means water profile will be falling. Okay, so here in case false. Okay, so there are many methods to derive this equation of dy by dx equal to s naught minus sf 1 minus q square t upon ga cube. Okay, so we can choose any methods, but we have to remember this equation because it will be useful in solving various questions. Okay, so let's derive dynamic equation for gradually varied flow. 1 second. For gradually varied flow in rectangular channels. So in rectangular channels, what we have is hydraulic radius is equal to weighted area by weighted perimeter. Means what is area? Area is b into y, and what is the weighted perimeter is b plus 2y. Means we can write it as by upon b, because if we assume that the depth of the flow is too small, then this 2y term becomes small. Okay, so it is always equal to b. So the hydraulic radius comes out to be y. Now putting this equation in Manning's equation, this value in Manning's equation, we get q equal to 1 by n to area into velocity is r to the power 2 by 3 and s to the power 1 by 2. This is the surface slope. Okay, so what is the area? Area is b into y, so this comes out to be 1 by n into b into y. What is r? R is y, so y raised to the power 2 by 3 and sf raised to the power 1 by 2. Okay, so it may be noted that the hydraulic radius has been replaced by depth of the flow. Means we have replaced radius by depth of the flow, and area we have written in another form. Okay, so this is the general case of the flow. If we assume that at normal depth of the flow, this discharge will be equal to 1 by n into b normal depth of the flow, and this channel bottom slope will be s naught raised to power 1 by 2. Okay, so if we divide this equation 1 and equation 2, okay, we will get this term is always get cancelled, this b term is cancelled. We will get s naught sf by s naught to the power 1 by 2 equal to yn by y to the power 10 by 3. Okay, let's write over here sf by s naught to the power 1 by 2 is equal to yn by y to the power 5 by 3. Means sf by s naught will be equal to yn by y to the power 10 by 3. Okay, this is the relation for rectangular channel. Okay, this we have derived using Manning's formula. Okay, we can also derive this relation using Chase's formula. Okay, now for rectangular channel, q square t upon g a cube is always q square. What is the value of t? T is top surface is equal to width of the channel. Okay, g is the acceleration due to gravity, and what is the area of the flow? Area is b into y, means b cube into y cube. So this comes out to be q square upon gb square y cube. What is the value of this q square by b square? This is small q, discharge per unit width. Okay, so this comes out to be small q square upon gy cube. Okay, this will comes out to be yc upon y whole cube. Okay, so we have to remember this relation q square t upon GA cube is always equal to YC upon Y to the power 3. Okay. Now substituting this equation of q square T upon GA cube in the dynamic equation of gradually varied flow, we will get dy by dx equal to S naught 1 minus yn by y to the power 10 by 3 upon 1 minus yc upon y to the power 3. Okay. We have to remember this equation. We will use it in solving numerical problems. Okay. Now we will see what are the types of slopes in the channel bottom. Okay, means bottom slope types. Okay, so the first one will be a critical slope, one is mild slope, another is a steep slope, horizontal slope, and adverse slope. These are the 5 basic classifications of slope. Okay, let's see it in short. Okay, we will study about it in detail in the next class. Okay, so what is a critical slope? Critical slope is that one in which S naught equal to SC. Okay, means what is this S naught? Okay, this S naught is the bottom slope, is equal to the critical slope. Okay, what is mild slope? Mild slope is when channel bottom slope is less than critical slope. Okay, means if this is the channel bottom slope, this is S naught. Okay, so the water flow surface will be less than this bottom slope. Okay, in this case the depth of the flow, normal depth, is greater than the critical depth. Okay, we will see it in detail. Okay, we will just looking almost basic of it. Okay, what is a steep slope? The third number is steep slope. Okay, steep slope is when the channel bottom slope changes drastically. Okay, it's called, means if this is the critical slope and the critical condition. Okay, this is the mild slope in which the bottom angle is very less. This is the steep slope. Okay, sorry, this is the channel bottom. Here this is the channel bottom, here this one is the channel bottom. Okay, so we can see that this angle is very small, so it is a mild slope. Okay, this angle is very large, so the flow here will take place in which the normal depth will be below the critical depth. Okay, and this is the critical slope, this is the mild slope, and this is the steep slope. Okay, the another one is a horizontal slope in which the channel bed is horizontal, means the S naught equal to 0, and another last one is a adverse slope in which the channel bottom gradually increases. Okay, and the flow here will take place over here. So this is the condition of adverse slope. Okay, so let's revise in lastly. This is the critical slope in which the depth of the flow, normal depth, is equal to the critical depth of the flow. This is a mild slope where angle is very less, and in mild slope the normal depth of the flow will be greater than the critical depth of the flow. Okay, this is the steep slope, okay, where water will flow rapidly in high speed. Okay, and here the normal depth will be less than the critical depth. Okay, the third one was the fourth one was horizontal slope. This is the channel bottom, which is does not make any angle with the horizontal. Okay, it is along the horizontal slope. Okay, and the third one is a adverse slope, in which the flow is taking place in this direction and the bottom slope is rising. Okay, we will see in the next class details about this slopes profiles. Okay, so that was all for now. Okay, thank you.